Good evening, and welcome to Public Observatory Night, presented by the Center for Astrophysics, Harvard and Smithsonian. My name is Nadia Whitehead, and I'm your host and a Public Affairs Officer here at the Center for Astrophysics. I'd like to welcome Elaine Hernandez, who will be providing American Sign Language interpretation for our program tonight. Thank you for joining us, Elaine. Elaine will be on screen with us the whole night to help make our event more accessible to viewers. We're pleased to present tonight's lecture, Cosmic Explosions, in a virtual format, live streaming to both Facebook and YouTube. We'll have time for questions at the end of today's lecture, but if you have a question during the show, just type it into the comments section of Facebook or YouTube. We'll get to as many questions as possible after the lecture. If you're interested in receiving our e-newsletter and information about future observatory nights, please make sure to sign up for our mailing list by visiting the link that's appearing on your screens now. It's also appearing in the comments section. Now, I'm pleased to present tonight's impressive guest speaker, Dr. Yvette Cendes, who will be presenting on explosions that occur in our universe. Dr. Cendes is a postdoctoral fellow at the Center for Astrophysics, Harvard and Smithsonian, where she specializes in radio astronomy and studies supernova and tidal disruption events, when a black hole spaghettifies and devours a star. During her time as an astronomer, Yvette has used the Chandra X-ray Observatory, the Very Large Array in New Mexico, the ALMA Observatory in Chile, and Meerkat in South Africa. Yvette specializes in science communication and has written for several international publications, including Astronomy, Discover Magazine, Scientific American, and Sky and Telescope. She is currently an astronomy consultant for Guinness World Records and is assisting with the 2023 edition of the book, which will be published in 100 countries and dozens of languages. She is known by many as Andromeda 321 on Reddit, where her Astronomer Here comments are read by millions around the world. Yvette earned a bachelor's and master's degree in physics from Case Western Reserve University in Cleveland, Ohio, followed by a PhD in astronomy from the University of Leiden in the Netherlands. She joined the Center for Astrophysics in 2019. Now, please join me in welcoming Yvette Cendes. Yvette, thank you for taking time out of your schedule to join us. I know you have a lot going on this month, so I'm going to let you get started with your presentation.
All right, thank you very much for that very nice introduction. Hello to everybody out there in internet land. I'm very excited to tell you guys today a bit about the research I do, which is on a lot of various giant space explosions. I'm going to tell you a bit about what these explosions are. So what a supernova is, if we might ever see one in our own sky, in our own galaxy, what that might look like, And I'm also going to tell you guys about tidal disruption events. So that's when a star wanders too close to a supermassive black hole and it gets shredded apart, basically, and what that looks like and how we know those sorts of events happen. So to begin with, if you stay up a bit tonight and look out into the night sky, this is what you will see. These are in our northern hemisphere, the winter constellations, which is dominated by the constellation Orion. So some of you guys might know these three stars here are known as Orion's belt, which form part of Orion, the constellation, who is the hunter in the sky. And if you look in Orion, all these stars, they're kind of different sizes, different colors if you look very closely. Betelgeuse is the upper left shoulder of Orion. Rigel is the right foot star. And if you follow a line down, if you follow down Orion's belt, it goes all the way down to Sirius, by the way, which is the brightest star in the sky. And I always thought Orion's very cool for several reasons, one of which it's a constellation that actually looks like, you know, the thing that it's supposed to look like. So that's very nice. But also there's a lot of interesting stars here, as I said, one of which is Betelgeuse. The upper left star. Betelgeuse is a star that we know is at the end of its life, and it is a star that is going to go supernova someday in the astronomically near future. So I'm going to tell you guys, what does astronomically near future mean, and what might that look like? So to begin with, I am a radio astronomer, as Nadia said, and I want to tell you guys a bit about what that means and why we do radio astronomy. So as you might remember from school, we have the electromagnetic spectrum, different kinds of light in different kinds of wavelengths. What we see is just a tiny fraction of that entire spectrum. So you go all the way from the highest energy of the gamma rays, then you have X-rays, ultraviolet, infrared, microwave, and the longest wavelengths that we look at are radio waves. The reason you have astronomers looking at different parts of the spectrum is because different parts of light give you different parts of the puzzle. Different kinds of physics give off different kinds of emission. So usually you do want to get, for a lot of events, information from different parts of the spectrum to figure out what exactly is going on in the system. The other thing that's really important to note about radio waves and why they're very cool, and hopefully I'm going to convert you guys to why radio astronomy is the best, but I don't have all the light that we have generated from objects in outer space reach the surface of Earth. So this is a general graphic that shows you visible light is just a very, as I said, tiny part of our spectrum. The very high energy stuff like the gamma rays and X-rays and things are blocked by the upper atmosphere and are best observed from space, which is probably good for us. It's probably best that we're not being bombarded by gamma rays and X-rays in our daily lives, but it does mean you need to use a space satellite to look at those frequencies. And then there's also a lot of the infrared is absorbed by water vapor in our atmosphere. A lot of that light will never reach Earth. But as you see in this graphic, radio waves, they don't really care about the atmosphere. They will come down all the way to the surface of the Earth. There's no better than if you just have a radio telescope in space versus on the ground. So it's actually, a lot cheaper than launching your space satellite or something like that and going up into space. But to give you an idea, so what does radio data look like? So this is, if you went out into an area which is a lot less populated than Boston, let's put it that way. This is what the sky would look like. You would see the Milky Way, you would see stars and maybe a comet and things like that. But if you had radio eyes instead of visible light eyes, this is actually what the sky would look like. It would look very different. So what we're seeing here, basically these splotches that you see in this picture, these are actually supernova remnants. They're basically, the remnants of these exploded stars. The little dots in the sky are actually not stars. They are actually the centers of supermassive black holes, millions and millions of light years away from us. So that's kind of an interesting one as well. We can see these things. The radio sky, as I said, is very, very different than what you would expect. And so, as I said, my research here is radio transients. I am basically using big telescopes, like this is the Very Large Array in New Mexico. And I am looking out at these objects to see what exactly is happening to them and how they evolve, how do they change over time, and things like that. I should note, because a lot of people ask, radio astronomy, we don't actually travel to the telescope. And this is actually pre-pandemic, we never even traveled to the telescope, or when that happened, it was before my career as an astronomer. Instead, you just download the data off the internet and you can analyze it in Cambridge and you don't have to travel. which is, you know, maybe a bit less romantic, but it is a lot more convenient, especially in the modern world with our pandemic precautions and things like that. So I was lucky enough to visit the VLA once. I gave a talk in Socorro and drove out and could see the instrument. It's a very impressive place. These telescopes, just to give you an idea of the sense of scale, this is the size of a building. Like, you know, you can kind of see here, okay, the stairwell as it's going up on the side. And you basically move these along giant railroad tracks to get the dishes into the positions that you want them to be in. And then you co-add these signals together to make the radio pictures that we basically use to get our information. So what sort of information are we getting? First, you know, to talk about supernovae, we're going to do a quick little primer of the evolution of stars. So we make sure that we all understand that we're on the same page here. So if you are a star like the sun, we have two tracks here. All stars start in a nebula and are formed from gas. If you're a small star, so something the size of the sun or something less than about 7 times the mass of the sun, your story is going to be that you are eventually, you know, you're fusing hydrogen into helium in your core. You're going to become a red giant. Once you run out of that hydrogen fusing into helium in your core, you are going to poof out your outer layers into a planetary nebula and leave behind something called a white dwarf. If, however, you are about 7 times bigger or 8 times bigger than the mass of the sun, and this is maybe only 1% of all stars we see in the sky. Most stars are not this big. What happens is you are going to burn through your fuel and you're going to become a red supergiant. And once you are running out of your fuel, instead of just poofing off your outer layers, you are going to die in a supernova explosion, leave behind either a neutron star or a black hole. And so the thing to remember here really is that large stars are really kind of the rock stars of our universe. So what I mean by this is they shine very, very bright. They don't live very long. They only live a few million years, whereas a star like our sun lives billions of years. And they also die in giant fiery explosions. So if we were to look at this supernova explosion and what exactly it would look like, you would see that you would have this giant explosion where basically the star goes and it explodes when it runs out of that fuel, and it sends a shockwave into its outer surroundings. So what this looks like is something like this is an artist's conception of what this would look like. But basically you have a shockwave that occurs, it spreads out, it's going to interact with everything surrounding it, and that is going to live off a ton of electromagnetic radiation. This is also going to be incredibly bright. So one supernova can be brighter than the rest of the stars in a galaxy. So one can outshine 100 billion stars in a galaxy. They can be that bright. The trick is, however, they are pretty rare. Like, you know, a galaxy of our size, we're only going to see maybe one supernova every 50 to 100 years on average. So, you know, you do kind of have to wait to see these and, you know, to see what exactly happens. So to kind of tell you guys a bit about how this goes. So, you know, if we go back here, and this is our view of the Milky Way, you know, the first thing you might ask me, by the way, is, so wait, you said 50 to 100 years. When's the last time we saw a supernova in our own galaxy? The answer is actually 1604. So 1604 was Kepler's supernova is what it was called. Galileo saw it, but he didn't have his telescope yet. So you could say, okay, but why didn't we see one for 400 years? The answer is you can look in this picture of the Milky Way. There's a lot of dust, you know, obscuring a lot of our galaxy. So what they always say is if you're thinking of something in our galaxy, you know, if it was the size of the United States, the amount we can see is basically like the state of Virginia. So a very small part of the galaxy as a whole. And so before you had things like radio telescopes where radio waves can travel through these dust clouds, it's much less of a problem. You definitely had supernovae that occurred in our galaxy. We just didn't see them. So then, okay, the next question is, what is the closest supernova that we've been able to observe since we've had telescopes? So if you look in the right here in this picture, this is actually a southern hemisphere picture. And the reason you can tell is there's these two fuzzballs on the right side, and this is the small Magellanic Cloud and the large Magellanic Cloud. These are satellite galaxies of our Milky Way. And if we zoom in more onto the large Magellanic Cloud, what you will see is this. So this is called the Tarantula Nebula and is the biggest star-forming region in our local galaxy group. It's about 170,000 light years away from us. So when I say light year, I mean the distance it takes for light to travel in 1 year. So this is 170,000 light years away from us. So you're like, okay, that's really, really far, even on astronomical scales. The trick, though, is there's nothing between us and this area. So this is an intense star-forming region. And if you want to find the biggest stars that we know of in our universe, you actually look up out into the Large Magellanic Cloud, because we don't have the dust like we have in our own Milky Way. So it's not that, there might be big star-forming regions like this elsewhere in our Milky Way, but we don't have a direct line of sight to them. So we don't know really much about them compared to the Tarantula Nebula. And the very exciting thing about the Tarantula Nebula is if you have a lot of big stars out there, and as I said, those are the stars that go supernova, then, you might actually see one. And in 1987, that is exactly what happened. So there's a very important supernova called Supernova 1987A, which is the closest since the invention of the telescope. So there were a lot of firsts that happened with Supernova 1987A. So first I'm going to tell you guys a bit about how this was discovered, because it's kind of a neat story. There was some astronomers down in Chile, one of which was University of Toronto's Ian Shelton was his name. I did a lot of my PhD work at the University of Toronto, so I feel obliged to always say that. And then there was a Chilean astronomer as well, and a few other people up there. And what happened, though, was Ian was working that night. He was they used to take data on these giant glass plates, sort of like the glass plates that are famous at Harvard in our library and things like that. And he was having trouble, though, with his observations that night. So he was like, okay, I'm just going to throw in the towel and go to bed, but I'm going to develop my plates before I do. And he went and was looking at the Magellanic Cloud. And he's like, wow, there's a really bright star on my plate. Before he went to bed, he was developing it. That's so bright. If I went outside, I should be able to see it with my own eye. So Ian went out and looked up and he's like, yes, that's actually there. And he called over another astronomer. He was like, do you see this? Yes. And they realized they must be seeing a supernova for the first time in hundreds of years that, you could actually see one with your own eye. My PhD advisor, he was a 13-year-old in Australia at the time. And he said, even in suburban Sydney, you could go out and you could look up and for about a month, you would see the supernova, even though it was 170,000 light years away. And because, this was a very well-studied area of the sky, there's a lot of things like we knew that we found this is the first case where we saw the star that ended up exploding. So this star, as you can see on the left, is the star and it ended up exploding. It was a blue supergiant star. I think I told you guys before, they usually red supergiants are the ones that explode. We'll revisit that in a minute. But yeah, there were some other things that happened that were very interesting with Supernova 1987A. Another one was we had neutrinos detected for the first time from outside of our solar system. So for those who aren't familiar with neutrinos, these are fundamental particles like electrons or, those sorts of things in the universe, but they are very, very light and they don't really interact much. So to give you an idea, like I'm going to give you a thumbs up. Normally, if we do this in person, I make everybody give me a thumbs up in the audience because that's pretty fun. Every single second, about 100 billion with a B neutrinos are streaming through the tip of my finger here. And so obviously, it's been going on all my life and, you were just aware about this now. It doesn't hurt you. But the point is there's a lot of neutrinos out there in the universe. The trick is, though, they're very hard to detect. They don't interact, as I said, very much with things. But what ended up happening, though, is so a supernova, when it occurs, it creates as many neutrinos as there are atoms in the sun. So a prodigious amount of these neutrinos. So even though they're super, super hard to detect, and even though Supernova 1987A is 170,000 light years away from us, when Supernova 1987A occurred, they saw, I believe, 18 neutrinos across 3 detectors on Earth, all within, a second or two of each other. So that was a huge, huge moment. As I said, first time from outside the solar system they were detected. As for how you detect neutrinos, by the way, so this is a giant neutrino detector in Japan. For a sense of scale, these guys are basically sitting in a boat. Those are 2 men in a boat. So, these are basically you have water that fills up this detector, and then you're looking for very faint flashes of light as the neutrinos come through and maybe sometimes interact with that water. The other thing, by the way, that's really neat about the neutrinos from Supernova 1987A is they actually arrived a few hours before the light did. And so, okay, you can't travel faster than the speed of light. What is going on here? The answer is when the supernova occurs in the center of the core of the star, the star is big. There's a lot of mass that light has to work through and that shockwave has to work through before it escapes from the core. As I said, the neutrinos don't care. They will just escape very, very quickly out. And, you can basically thus have a detector of neutrinos for supernovae in our own galaxies. This actually exists. You can go online. It's called Supernova S-News, Supernova Neutrino Alert Detector something. And if you just Google this, it'll come up. And you can sign up to receive alerts for neutrinos. If all the neutrino detectors on Earth go haywire, then you should run outside and maybe you'll be the first to see a galactic supernova. But anyway, so once Hubble was launched, because it wasn't yet up in 1987, took a look. And this is what Hubble saw in supernova 1987A. So what exactly are we seeing here? We're actually seeing a lot of complicated debris around supernova 1987A that existed before the supernova explosion occurred. So in the tens of thousands of years before the star exploded, it let all this gas out. So what you can kind of see here is if we have an artist's conception of what's going on, we have an innermost ring, this purple ring. So this is swept up red giant gas. We have this hourglass shaped figure. We have these two outer rings. And these days, what we think happened is supernova 1987 was a red supergiant star, underwent some sort of merger with another star in roughly tens of thousands of years pre-explosion. And then it was a blue supergiant star because of this merger, and then it exploded, fairly astronomically quickly after that explosion happened. So, we had a star that shouldn't have exploded and did explode, and we had this merger. Most people think there's some sort of, obvious relationship there, but we don't really know the details because, we don't really see too many of these out there, unfortunately. Anyway, so the supernova happened and, that was 35 years ago. So what's been going on since? So, what I always explain, what are we doing in astronomy? On the left here, you see supernova 1987A in 1987. On the right here, you see a picture of me in 1987. So what we do in astronomy is, it's basically what an alien anthropologist would do if you suddenly came to Earth and you were like, okay, I see a little small cute human and now I see this person, like, gee, what happened? Like it started off so well. So, you would go and study, a human person over years and see how they grow and get a little less cute and things like that and learn about stars. And you would then learn how this, entire person evolved into the person you see today. That's really what we're doing with supernova 1987A. So we're studying how does a supernova become a supernova remnant? What happens as the shockwave goes outward? Things like that. So I observed supernova 1987A as part of my PhD research. This was using ATCA, which is the Australia Telescope Compact Array in Australia. Southern Hemisphere, we couldn't use the VLA in New Mexico to observe it. And this was part of a process that started in 1992 and, it went up to the late 2017 was the last published one. Though I will note, we actually did just get data last week. I saw it. It looks beautiful, but I'll show you what we have so far because it's pretty neat. What you can see here is, as I said, there's a shockwave going outward. It's interacting with all the material around it. So you see this smoke ring. This is basically created, all this radio emission that you're seeing, from electrons spiraling in magnetic fields. It's called synchrotron emission. And that's really what we're just studying is as this shockwave goes outward, it keeps hitting material. It keeps lighting up this circle as it goes further out and out. And the cool thing you can also see is roughly 2003, it starts getting a lot brighter, a lot faster. And that's because there was that innermost purple ring that I was showing you guys in that artist conception. We think that's basically when the shockwave slammed into that ring and started basically obliterating it. So if you want to see sort of a full picture of what this looks like. So this is actually, okay, I do cross stitch. And this is basically, I cross stitch supernova 1987A. This is the first figure from my PhD thesis, the paper that was on this. And it is completely all astronomically accurate. And, when else am I going to have the excuse to show this off, except if not in a public lecture? So what you can see here is supernova 1987A. It started, if you start in the upper left corner, very small, not very bright. Then it gets brighter, it gets bigger, it expands outwards. Over time, you're going just left to right. And this is what we see today. We kind of see this donut structure as this shockwave. I think it's now actually gone outward and it's spreading out into the medium surrounding outside of that innermost donut ring. And we're going to see, you know, what happens next as it keeps expanding, keeps getting brighter as well. That's kind of an interesting one to note that, you know, it's now brighter than it ever was when the original supernova explosion occurred, just because it's been running into all this material. So to kind of wrap up Supernova 1987A, people always ask sort of what's at the center of Supernova 1987A. I told you guys that you either have a neutron star or a black hole left behind. We have recent evidence that there was a pulsar wind nebula. So if there's, you know, a neutron star interacting with some dust around it, that might be in the center of Supernova 1987A. It's not really yet confirmed, but I think more and more people are like, you know, you keep adding a few grains of evidence as you go on in astronomy. And then eventually it's like, well, there's this huge body of knowledge. We're not there yet. I think we are heading in that direction. You can ask me though, what about a black hole? You said a black hole could occur there. Basically what happens is we know a neutron star was created because that's, you know, when the neutrinos escaped from there. And then what happens is, though, within a second, a neutron star would then further collapse if it was sufficiently massive into a black hole. We don't think the original star was massive enough for a black hole to have been created. So we think we're really looking for a neutron star and not a black hole in the center. To move on, though, to, you know, another explosive topic, I suppose. I'm going to tell you guys first a little bit about black holes, and then I'm going to tell you about how black holes can destroy stars that get too close. So here is a picture of a black hole, which is much, much more massive than anything that would ever be created in a supernova explosion, like in 1987A or something similar. This is a picture of a black hole that you guys might have seen recently because it's definitely made the rounds. And it is our picture of a black hole called M87 star. It's about 53 million light years away from us. And it is billions and billions of times more massive than the sun. It's called a supermassive black hole. And this picture was created by the Event Horizon Telescope. To give you guys an idea, if you're looking at this image, the orbit of Pluto is the innermost little tiny circle. Had a mouse, I don't know, yeah. So this innermost tiny circle here. And that is basically, you know, if you were to drop our sun inside, you would never ever see it on this scale. These things are massive. We also think every single galaxy out there has a supermassive black hole at its center, which is very cool. The other thing that's very interesting about M87 is it's also shooting out what we call a relativistic jet. So what is it's basically a jet of material that is at relativistic speed. So, you know, over say 20% the speed of light. I think this one's like 50 to 60% the speed of light. Relativistic effects come into play, and it's 5,000 light years across. And you can actually see this, like, you know, Hubble looked and you can physically see this jet going outward. So it's really, really a very interesting system. We don't really understand a lot about these relativistic jets yet. What exactly is creating them? It's clearly, you know, obviously supermassive black hole, very unusual environments, but there's still a ton of questions that are unanswered in astrophysics about these relativistic jets. So, you know, now we know the parts of the supermassive black hole, and we're going to move on to what happens when a star wanders too close to one. And that is called a tidal disruption event. So I have a video here, which I think is going to be played. Yes. So as I said, this is a supermassive black hole artist conception video, obviously, of what one looks like here. And what we see is we have our supermassive black hole and a star. You know, maybe it interacted too close with another star. It got sent on a different orbit. This orbit is going too close to the supermassive black hole. And it is basically going to start first getting pulled apart into a more, instead of a circle, it's going to be a thing. This is called spaghettification. That is an official scientific term for you. And then it is going to basically get shredded apart. Half of the material is going to go into an accretion disk that forms and falls into the black hole. The other half is going to go into this outflow, is what it's called, of material. Sometimes they launch jets, the little things going up and down, as I said, relativistic jets. Most of the time, you just get this relativistic outflow of material that you can see here. And these are very, very exciting. They're very rare. You know, you'll get one of these TDE events in 1,000 supernovae or something like that. They're very uncommon, but exciting. Let's put it that way. And yeah, and this emission can last for a very, very long time after the supernova. So what do I do with TDEs? So first of all, most TDEs these days are not discovered by radio astronomers. What we're usually doing is we have these optical surveys now, where basically astronomers are looking at a ton of galaxies every single night, looking for usually transients. So like a supernova went off in that galaxy or something. And then you basically just compare to the previous night. You do this for a lot. These days, these supernova surveys will find about 18,000 supernovae every single year. I think, yeah, last year was 18,000 or so, which is, of course, an incredible number. And of those, about 1 in 1,000 will be a TDE. You basically can tell because, as I said, they're at the center of their galaxies, is the first kind of clue. And then you can take a spectrum, look at the elements that are in that, and it's going to be very different than what you expect from a supernova spectrum. When this happens, you know, we get alerts on these things. It's called astronomical telegrams. Obviously, you don't get a telegram anymore, but used to be. You would literally get a telegram at the observatory saying so-and-so discovered this and that. And we will trigger the VLA. It's called a trigger, where we're not, you know, really in the normal program because it's something special has happened. We will point the VLA out of its normal operations at this new object. Usually what happens, though, is it's not that you're like replacing someone. You've applied in advance that I am going to want to observe X number of these events. I have a very good reason thinking we're going to see this many number of events. And then when you trigger the VLA, then, you know, you can get your time and you're not like kicking someone off or something mean like that. But anyway, so what we're doing, though, is the reason we're interested in this radio emission is once the radio emissions start, it can last for years and years, because it's basically the same principle as you saw in that Supernova 1987A video. As the shock wave goes outward, if there's any material from these outflows, which we know there is, it's going to interact with everything surrounding it in this galaxy. So from this, we can actually extract a lot of information, even of these things. So we can tell the radius of the outflow, we can tell its energy, we can tell its magnetic field, we can even tell the density of the material it's plowing into. So this is all, you know, very cool physics that's already been figured out by people who are more clever than me. And I take my radio telescope and I figure out all these parameters to try and figure out how exactly these tidal disruption events occur, how exactly the system is evolving. So there's kind of two main categories of supernova, of tidal disruption events. So I'm going to tell you guys a bit about them. The first example is one called Swift J1644 plus 57. Astronomers, you know, we don't always have the best names. So to tell you, Swift, it's called this because Swift is the X-ray telescope that discovered it on March 28th, 2011. 1644 plus 57 are the coordinates. So now you know how, if you ever see a confusing name, it's probably in astronomy, it's probably coordinates in the name there. But so the interesting thing about this was, so as I said, this happened in 2011. TDEs, like people had the idea that they might exist. There were some potential things. And then Swift discovered this one thing, and it was basically a gamma ray burst, 3.5 billion light years away, gamma ray, X-ray. We pointed the group I'm in now pointed the VLA to it, and it was the first radio detection of a tidal disruption event. And this all pointed towards something incredible, which nobody was really expecting before it occurred, which was that basically a TDE event had occurred. A star got, you know, destroyed by this black hole, and it launched a relativistic jet, which nobody really was expecting, as I said. So it was really quite a shock. And then the thing that was even more incredible is after about a year and a half, the jet turned off. So, you know, normally these jets, to get to something as big as 5,000 light years across, it's been around for thousands and thousands of years. Something that only lasts a year and a half, like that's a postdoc, you know, like that's a pretty short time on our lifetimes even. So it's an incredibly important data set for, you know, these astronomers interested in things like relativistic jets and how they work, because we actually have the start and the end in a very manageable timescale there. So that's pretty exciting stuff. We can still detect this in the radio, though, because as I said, there was a shock wave that also gets created by this jet and stuff, still goes outward, and we can still observe that today. And so, you know, more cross stitch. So on the right, this is what most things that are 3.5 billion light years away, they're just going to look like a point source. You're not going to see too much, but this is what actual, data from the VLA looks like. On the right is my VLA image, and on the left is my cross stitch. So, by the way, when I have these images, if you see the little circle here, that's called the B model. That's basically the resolution that we have. So as I said, you can see it's a point. It's roughly as big as the circle. So that's kind of how that works. But what we're really doing in radio astronomy, once you have these things where they're just like this, we're looking at multiple frequencies. We measure the brightness, called the flux in radio astronomy, of this point source. And then we basically are doing this at multiple frequencies and applying our models to this to extract that information I was telling you about earlier. So, we've been studying SWIFT-J 1644 plus 57 for quite a while now. It's, we passed the 10-year anniversary this year, so that was quite the milestone. I had a paper published this year. It's still just expanding outwards, things like that. There's a ton of questions still about SWIFT-J 1644 plus 57, about that relativistic jet and things like that, but it's kind of an interesting thing. So we saw this event, as I said, it was incredibly bright, everything like that. There was another one of these jetted TDEs also seen in 2011, but at much greater distance. And then there was a third one seen in 2011, also at greater distance, and we have not seen one since. So this is kind of a problem, you have to do in astronomy whatever the universe gives you. And I checked, and you really can't order these on Amazon. So what exactly is going on with these jets? It's really hard to say until we get another event what exactly is going on. Right now, though, it looks like, maybe only 1% of these TDEs launch relativistic jets, just because statistically, you kind of look, we've seen this many TDEs that don't, and it might be much less than 1%. We don't know. We're just kind of at the mercy of the universe and what the universe sends to us on this. So to move on, though, I just said most TDEs don't launch these jets. So what do the rest of them do? So as another example, I'm going to tell you guys about another TDE called AT 2019 DSG. So this is basically, just a transient. So we give it a name. By the way, so the way it works is when you have a transient, you give it the year it was discovered in, so 2019 in this case, and then you start with A. So supernova 1987A was the first supernova in 1987. That's pretty self-explanatory. DSG, as I said, you can tell we're starting to discover, this was discovered in March 2019, and we're already on 3 letters. So, that last year they got up to 4 letters. So it's like 2020 A, B, C, D or something. It definitely is an object. So anyway, this is a pretty cool object. This is a pretty cool TDE because it was a black hole about 30 million times the mass of the sun, 750 million light years away. When you're talking about these very explosive events that are very bright, we start talking at great distances. This is pretty close for us, honestly. And this is a pretty cool event because it's the best studied radio tidal disruption event to date. Especially for something that just launched what we're calling an ordinary outflow, similar to what you see in supernovae, not with a relativistic jet. And also, if you go to the CFA website, we had a press release because this paper just got published this week, and you can go read a lot more about AT 2019 DSG and a lot of interesting things that we discovered. We proved there was another group that said that they thought a neutrino came from it, and we were like, look at our amazing data set. We don't think it came from it. This is science. This is what we do. But anyway, so what you can also tell, though, is, we have these various tidal disruption events. We're really sort of just we still have less than 20 in the radio, but we can start putting them together and get some populations going, see what's going on within tidal disruption events and kind of how they work. So the first thing to note that's very interesting is it looks like there's 2 populations of TDEs emerging. One of these populations has relativistic jets, things like that. So if you're looking in this plot, what I'm plotting here is velocity here on the bottom. This is the dividing line between relativistic. So as I said, many percent the speed of light, non-relativistic, just kind of going at, only a few thousand kilometers a second only. Yeah, I know. Astronomy's crazy. And then you have the energy. So what we're seeing here is these are very fast, very energetic objects. The interesting thing here to note is as SWIFT-J 1644 plus, this is actually the direction that this data goes. So it's now becoming non-relativistic. It's slowed down quite a bit since its original explosion or disruption. But most TDEs, though, on this plot are going to be down here. So this is where the normal supernovae live that are kind of like a supernova 1987A, like that video I showed you before. So they're not very, very energetic, not very fast events. So these are kind of more normal shocks. These are very energetic shocks. This is similar to gamma ray bursts, which are basically very, very violent supernova explosions that launch relativistic jets. So as I said, what percentage is in what fraction? We don't really know that yet. There's still a lot of questions here. As you can see, we don't have that many objects yet on this plot. We really need to get more data to figure out what exactly is going on. The other thing that I think is really, really neat about tidal disruption events is we can also start learning about the densities surrounding these just by studying surrounding these supermassive black holes, just by studying these shock waves. So this is the radius on the x-axis here and the density, so here in centimeters. And so on this plot, just to point out a few objects here, this blue one is Sagittarius A star. So that's the black hole surrounding the our own Milky Way. So sort of the density profile as it goes outward. This light blue one here is M87. So the Event Horizon Telescope black hole that I showed you guys the picture about earlier. And you can see that's a less dense black hole environment than our own. But then you can start overplotting these different TDEs. So Swift J1644 plus 57 is similar, to M87. AT29 DSG definitely falls off much more steeply than our own Milky Way. And the interesting thing and fascinating thing to me about this is you will note that compared to our own Milky Way, we actually know the density profile of these galaxies that can be hundreds of millions or even billions of light years away from us better than we know our own Milky Way. Why is that? As I said, there's a lot of dust between us and the center of the Milky Way. This is a very hard measurement to make. But I just think it's astounding that these days, if you're interested in these environments, this is the way to go. This is the way you're going to study this. So I think that is just really, really exciting. And seeing this plot fill out over time is just the neatest thing ever, in my opinion. So looking ahead in tidal disruption events and kind of what we have, or where we're going in the field and stuff like that, I did kind of want to tell you guys a bit about the future. So the first thing is we now have a VLA program, which started in November 2020. I am a member of a pretty large team. And the idea is that we're now doing the first comprehensive radio study of all the local TDEs. It kind of used to be that you'd have so-and-so would have this many triggers on the VLA, so-and-so would have this many. We've now all combined forces so we can all go after these objects and make sure that we catch them all, to make sure that, it's a very precious resource to get telescope time and see what's going on there. I can tell you, we've been going almost a year. We've been seeing about the number we were expected. So to give you an idea, I don't know how much I should say here, but by the end of 2019, officially in the published literature of all the TDEs that have been looked at in radio, 8 were detected, 22 were not detected. We're at roughly that percentage right now for detections of radio TDEs. A lot of them don't, in the initial first months, have any radio emission. And so a lot of people assumed earlier that it was okay, you're just not seeing any emission. Maybe you're not having outflows strong enough. Maybe it's not a very dense environment, things like that. Or is it? So this is kind of something that I don't know how much I should go into, but it's very exciting, so I'm going to get into it. I have actually been working more and more on late time observations of TDEs. So not me, another group has published recently data showing that there's some TDEs out there, which you're not going to see anything for the first few years, and then you're going to see them become radio bright. So far 2 have been published. I have been leading a group using the Meerkat telescope in South Africa, which has taken its first observations of late time TDEs. I can tell you we have detections. We're still analyzing that. And yeah, it's just been a very, very exciting project to be involved in this stuff. We also have a lot of late time VLA data because, we've been around the block. And yeah, so to give you an idea what it's like to be a radio astronomer, one of these TDEs, it was detected in 2018. That's probably already more than I should say. But there was no radio detection, pretty good limits on it. And it's now suddenly got very bright. 2 days ago, I was staring at this, you know, honking bright source, in my opinion, at least as a radio astronomer, on my screen. And we're now frantically trying to trigger the VLA and everything like that. And this is really, you know, it's going to sound very geeky, but it's what I always dreamed radio astronomy would be like. And it's just so cool to finally be able to do this, to have a discovery where you're the only person on Earth who knows what that is. Like if you're a young person thinking that maybe I'm interested in astronomy, something like that, that's really the feeling I'm going to sell you guys on. The feeling when you know something on Earth that nobody else knows. It's just really something else. Anyway, so TDEs are cool, but I'm going to wrap this up so we can, you know, have a little Q&A session here and go on back to the original slides where I was telling you guys about Betelgeuse and it might explode. And you might have heard that Betelgeuse was behaving a little strangely recently. So I just wanted to touch on this very quickly because it's usually a question that comes up. So it's beginning the end stages of its life, but the stage is thought to last thousands of years. And it had a very, very big dimming period in 2019. Everybody freaked out because they're like, oh my God, Betelgeuse will explode. I don't know a single astronomer who was like, I think it's very likely to explode. The trick is we always just hedge our bets in astronomy. So even if it's like 99.999% chance that it's not going to explode, it's like, there's a very slight chance. So I'm not going to 100% say that it's going to explode. Anyway, this is a light curve of how Betelgeuse has changed over time. As you can see, it's now back at its regular brightness. What we think happened is, so people did go and take data of Betelgeuse, January versus December 2019. You can see that the star itself has changed shape a little. It got a little dimmer on its side. And what we think happened was actually a dust cloud got ejected from the star itself. So supermassive supermassive stars at the end of their lives are very, you know, tumultuous things. They'll poof off gas all the time. They'll do things, as I said, there were those rings around Supernova 1987A. They do a lot of this sort of thing. What we think happened was Betelgeuse had one of these dust clouds poof out and basically obscured its line of sight between Earth and the star. So that's why it looked like it dimmed for a few month period. And as a result, though, like, you know, this is just something that happens. As I said, we think Betelgeuse, it's still got at least tens of thousands of years to go before its death. As a quick aside, just in case anybody's curious, like what is the most likely star in our immediate vicinity to explode? It's actually a star you've probably not heard of called Eta Carinae. And the reason you haven't heard of it is it's in the southern hemisphere versus Betelgeuse, both northern and southern hemisphere can see it pretty well. And it's, as I said, pretty nice bright star in the sky. So it's a star that has 100 times the mass of the sun, and it's lost about 30 times the mass of the sun in its life. And there was, in the 1800s, a great eruption was seen that made it the fourth brightest star in the sky and then faded below naked eye visibility. So even more extreme than what we're seeing right now from Betelgeuse occurred from Eta Carinae. So that'll be kind of an interesting one. Keep an eye on. You might have to go to the southern hemisphere if you want to see a supernova with your very own eyes. I guess we'll just have to wait and see what happens. So to wrap up this talk, I just want to, you know, have some final thoughts here. Radio astronomy is a very powerful tool for understanding the later stages of these transients, how they evolve after they occur, after the emission fades. We can see this in Supernova 1987A as the shock wave goes out and interacts with other things. For TDEs, we're really still just learning about this population and what exactly is going on, but we can learn a lot of information from the radio that we can't learn at other frequencies, so that's very important. And as an aside, I should mention, because I do science writing, I got a little frustrated. I couldn't find an article on TDEs that I liked, so I decided to write my own, and it's going to be in the December 2021 issue of Astronomy magazine, so I wanted to plug that really quickly in case anyone's interested in this topic in the audience. You should be able to get it either online or at something called a newsstand that, you know, parents can explain to their kids what that is, roughly in about a month from now. So keep an eye out for that. So just to, you know, kind of leave you all with a final thought, let's go back to the beginning of the talk where I showed you guys this is Betelgeuse, Rigel, Sirius, you know, the constellation of Orion. So, you know, as we're going into winter and if say you signed up for those neutrino alerts, what exactly would happen if Betelgeuse, you know, maybe the astronomers are wrong and it did explode? So, you get your neutrino alert, you go outside, and then this is what your sky looks like. And you go outside and you're going to wait and you're going to wonder what exactly is going to happen. And then there, you would suddenly see a supernova explosion happen. You would see that for the first time in our own galaxy since 1604, the first in 100 years. And then, this is something that's bright enough. It would be visible for months and months in the sky, maybe bright enough to see during the daytime. And it's definitely something that, we can tell our grandchildren about someday. So thank you very much. I'll take any questions.
Okay, thank you, Yvette. That was fascinating. We did have questions come in while you were speaking, so we're going to start pulling those up. But for everyone else, if you have a question, just type it in to the comment section of Facebook or YouTube. And we have about 11 minutes left till we end. So we're going to take as many questions as possible before we end. So let's see. Let me go ahead and pull up a first question. So from Tony on YouTube, 170,000 light years. That's 6 trillion miles. How do we really see this far?
Oh, well, so the trick is, there's, as I said, nothing between us and there. It's actually just so bright that we can see it because the light, there's a lot of stars in the Large Magellanic Cloud, and combined, they are quite bright. You can see it with your naked eye. I've seen it if you go down to the southern hemisphere. To give perspective, though, so the furthest galaxies we can see are actually even further. The Andromeda Galaxy, if you go out, you can see, even though that's 1 million light years from us. So, get enough bright things together and this can happen. Yeah.
All right. Thanks for your question, Tony. Okay. Next question from Maya on Facebook. What elements do you see in the spectra of a tidal disruption event?
So I have to confess, I really need to look this up because I'm not an optical astronomer. I just know that they're unique. So like normally if you have a supernova event that happens, I can tell you the things you can see because you're going to run out of hydrogen, right? You're not going to have too much hydrogen left compared to other elements in the supernova explosions. I'm going to tell you a TDE is going to have a lot more hydrogen in it, for example, because that star has not actually burned out all the fuel at the center of its core. So that's one example of something you might see. But yeah, the specifics, I'll have to ask someone.
No problem. Okay, so next question from Phil on YouTube. What are the timelines in these explosions?
That is a great question. So for something like a supernova, the supernova event itself is like that. As I said, it takes a few hours for that light to reach outward. But the brightening is just going to be a few hours. It's going to be a peak brightness. The fading can last, years, depending on how close it is to you and how luminous the explosion was. The tidal disruption event itself is also quite short. So we think the fusion, when the star is no longer burning or shining, is just a few hours for it to be pulled apart and to have this no longer happen. So that's, a lot of these explosive events, they happen very quickly. The fallout or the follow through, is much longer. Like supernova 1987A, as I said, it's getting brighter right now in radio. Probably in 100 years, you're still going to be able to see it in radio. This emission can last much, much longer.
Wow. Okay, some more questions are coming in. Let me see. So Stephen on Facebook, could Betelgeuse collapse to a black hole? And thank you, excellent presentation.
Oh, thank you very much. I believe Betelgeuse is not big enough to become a black hole, but we should probably look this up real quick. So, because it has to be 18 solar mass. I don't think Betelgeuse is quite there.
Okay.
Yeah.
I'll go ahead and get to the next one. Interesting question from Chief on YouTube. Does moving an antenna a few feet along the track make a meaningful difference?
Yes. Okay. There's kind of two parts to the question. By the way, I looked it up and we don't think Betelgeuse is going to leave a black hole behind. But anyway, so the reason it matters, so we will actually move them miles to get different configurations. And that basically changes the resolution on the sky that you see and then the field of view. So if you're looking like, you're interested in just like a nebula nearby, mapping its emission, you're interested in a different configuration than us who are looking very, very far away, trying to get the maximum sensitivity, things like that. The reason a foot would matter is so we know the positions of these antennas like to within a foot when they're placed out on these tracks for the VLA. Because we are co-adding these signals together, you have to be very precise. You have to know the measurements exactly. So if that was wrong, you would basically screw up your image and you would not get these very nice little point sources that I've shown you guys and things like that. So yes, a foot in itself doesn't matter, but a foot is not where you expect it to be. That really does matter. So.
Okay. Thanks for your question, Chief. Next, from Erica on Facebook. Do supernova explosions only explode in that donut shape, or are they spherical and we just see the outer edge?
That is sorry.
Oh, no. Let me see. There's a part 2 to her question. If they're donut shaped, presumably we must be edge on to some of them. Okay.
So this is actually a big question in the research if you study how supernova evolve. So supernova 1987, like there's still, first of all, a shock wave going out. We just don't only see that donut because that's the highest density region. So that's really what's dominating what we see in radio. We don't think the shock, we think it was an asymmetric shock, so it wasn't perfectly circular, just because if you look, that donut was visibly brighter on one side than the other side, right, as it was going outward. So that kind of tells you some of the shock is probably faster than the other side, right? Because why would it be brighter, faster on the other side? So how much this matters is said, like, most of these are so far away, you can't see the detailed information. So if you're studying supernova shock waves, you're usually just going to assume spherical because that's easy, but that's probably not always physically accurate. But the supernova light itself, when it first happens, like it's really going to, even if there's a little bit of dust, you're still going to see it because it's just so honking bright. So.
Okay.
Yeah.
Next question, Jonathan on YouTube. Or actually, it looks like someone related to Jonathan. My name is Luke. I'm 11 years old. What can I do to have a career in astronomy?
That is a great question, Luke. The first thing I would say is study math and physics. My background is in physics. I'm not saying you have to, by the way, be like the best mathematician to be an astronomer. Like I always just got B's in math. I was never that good at it, but I really liked the field, so I kept at it. And it's, showing up every day and working a little bit at it is really what counts in the long run. Also, these days, computer coding is really important. If you have the chance to just play around and learn a little coding or maybe even take a class, that is going to be super, super useful for when you get into college and study these things. So I hope that helps Luke go on the right path there. So, and yeah, just listen to talks like these, ask a lot of questions. I'd say that's also just keep being excited.
Yeah. Good luck, Luke. Okay, from Sean on Facebook. Has a mass neutrino event ever caused a search for a cosmic event? Can the direction of a neutrino be detected?
So there have been directional so there was an object called a blazar that was associated with a neutrino a couple years ago. So this was a blazar is basically when you have one of these relativistic jets from a supermassive black hole pointed directly at you, and it flared, and they think they saw the neutrino. It's very, very hard to associate neutrinos with specific events. So as I said, like we just got into a little scientific kerfuffle, I guess. It wasn't like a fight or anything. It was just like we had data on this TDE and we're like, we don't think a neutrino came from this. It's really hard. Like, yeah. So people have tried, but it's still very much a field in its infancy, I'd say, in that sense.
Okay. Let's see. Next question from Calum on YouTube. Is it possible that there are rare, completely different types of stellar explosions that we don't know of yet? Or have we more or less mapped out the landscape?
I'd say the amazing thing is whenever people think that they've already figured it out, there's always something new. So there's a new kind of explosion right now they're called F-bots, so fast blue optical transients. And this is basically a new explosion that was discovered, and it was like too bright to be a supernova, not bright enough to be a TDE. And we frankly just still don't know what these are. There's maybe like 4 of them, I think, right now in the literature. So, What are FBOTs going to turn out? Are they going to be maybe something completely different? We really don't know. This is really the early days. So yeah, there's still always things popping up that are very interesting and you don't know at first glance what they are. So.
Okay, so I'm going to pick one more. This is going to be our last question because it's about to be 8. So Stephen on Facebook, are thousands of low orbit satellite constellations creating problems for radio astronomers?
Yeah, they're not going to be a good thing. Okay, so a lot of the the main mega constellation right now is going to be at about 10 gigahertz, which is smack in the middle of the band I need to figure out these TDE observations. So when that happens, if nothing is done about it, I'm basically, we just lose that frequency to man-made interference, and you're no longer going to. Can you work around it? Yeah, but it's never going to be as precise data. Like you might have your peak be right there, and then it's just going to be like, well, that data is gone to you. So that's unfortunate. There are some recommendations to the UN that, we could have rules, international agreements that just don't beam these things to specific areas that have radio telescopes. I'm not sure how easy the engineering is on that, presumably harder, but I hope, if enough people are aware of the problem, then, we can go forward and figure out a solution that we don't lose the resource of the night sky. Because as I said, radio astronomy, we don't even have to go into space to do it. So that's really important to me, at least personally, that, it's very, doing a space mission, look at how long James Webb or something like that takes versus we can just do it on the ground. It would be real a shame if, the sky gets too full and we can't do that anymore. And, I hope someday they'll give me enough money to build a radio telescope on the far side of the moon. But until then, realistically, we have to protect what we have. So
that would be amazing. Okay, so we're going to close out Observatory Night. Thank you so much, Yvette, for joining us. And thank you for everyone who watched online. If you enjoyed this evening's presentation, I want to encourage you to support the Center for Astrophysics and consider giving. We're going to pop up a link on our screens right now. It's also going to appear in the comments section, so that's where you can go and donate if you have a chance. Any amount will help support the important research like Yvette's that goes on here at the Center for Astrophysics every day in an effort to answer humanity's greatest unresolved questions about the nature of our universe. We look forward to seeing you again for our next Observatory Night, which will be announced at a later date on our social media channels. Visit our website, cfa.harvard.edu, for more information about the Center for Astrophysics. Thank you, everyone, and good night.